Natural gas has become an increasingly important resource as it is clean burning, abundant, and versatile. One of the downsides to collecting this resource, among others, is the wastewater it produces. This wastewater, or brine, is a result of oil drilling and hydraulic fracking. It commonly consists of injection water, some oil, and salt. The average well in North Dakota produces 18 barrels of brine per barrel of oil and 3 barrels of brine per barrel of gas. Brine spills happen for a variety of reasons and are prevalent and often unreported. In 2014, there were an average of 42 brine spills a week in North Dakota. Brine spills cause a loss of structure in soil, which in turn damages the water's ability to infiltrate the soil, and plants are less able to take up water in sodic soils and even lose water to the soil through osmosis.
Now, normally when sodium is spilled onto the ground, it's very immobile because it's very water soluble. It can move a very long way in groundwater and in surface water. And it will move until it finds a negatively charged clay colloid. And it'll stick and cause problems for the local microbiome. Our solution is to remove these positively charged sodium ions by finding a calcium positively charged cation to knock them off. We know that it will knock them off because these calciums are more attracted to the negative clay colloid than the sodiums are. So when we introduce these, it knocks these off, and the sodiums come off in the groundwater and are washed away. Our calcium source is going to be gypsum or calcium sulfate. This is very cheap and it's fairly water soluble so that when it's laid on the top layer of the ground, it can soak in and work its magic. The way we know how much calcium sulfate to use is that for every calcium that we add, we remove 2 sodiums. Now when this ends up in water, this is cleaved here, solubilizes.
The aim of our project is simple. We know that gypsum is one tool used to remediate sodic soils. Within this, we'd like to explore how much of a difference it makes to remediate immediately after the insult becomes an issue, or if it's fine to wait before remediating at all. With this question in mind, we set up 6 samples for our experiment that we divided into 3 different columns with 2 in each column. In the first column, we had our 2 controls. The top received no remediation, but was insulted with the saline solution to simulate a sodic input from fracking. The bottom sample was neither remediated nor insulted. In the middle column, both samples were insulted with the same saline solution on March 8th and subsequently remediated the following Monday after the insult. The third column, over on the right, was insulted at the same time as all the others, but were not remediated until a week later on March 15th. To keep track of the experiment, we watered and measured the plant's pH, EC, and tray weight every Monday, Wednesday, and Friday starting on February 20th.
During the first week, electrical conductivity never reached 4 decisiemens like a normal sodic soil should have. We suspect this is due to sampling issues from not digging deep enough in the soil to sample for fear of disturbing plant life growing on the surface. Electrical conductivity did not seem to differ between the fast and slow remediation until about after the second week when the slow remediation started. By the time the 5th rolled around, the soil had reached approximately the same electrical conductivity, and the spike in electrical conductivity from the slow remediation had reached levels approximately that of the fast remediation. On the 5th, the soil was tilled, thus distributing the remaining salts throughout the volume of each sample, and new seeds were planted. After this point, you can see that the electrical conductivity of all samples experiences a slight spike again, mostly due to salt being moved back to the surface by tilling. By the time the experiment was over, it was difficult to say whether we had done much good between fast and slow remediation. However, By looking at the graph, you can experience that on average, doing nothing, or the gray line as our negative control, was comparable to slowly doing something. The biomass results slightly contradict this result in that plants were growing in the samples that we remediated after the fact, all except the slow remediation sample number 1. There was no other difference between fast and slow remediation that we could discern from this data. It should be noted that when no remediation was done, no biomass was able to grow after tilling.